Hello to all of my DC environmental students. I hope the year is going well for you. I know that Mr. Womack is going to be out for a little while with the arrival of his new little one, and we're super excited about that. You may not be super excited to be having to watch these videos that I'm making, but here you go. This is going to hopefully help you understand the note material a little bit better. And if you have any questions, feel free to email me or be in touch since I know your teacher's going to be out for a little bit. And so what we're going to do today is we're going to go over the energy and ecosystems. And a lot of this may be review for you from freshman year, but then there's maybe some things that you've never covered before. It's definitely a little bit different than just a regular biology lesson. And so we're going to start off with just a little bit of energy background. If you've had physics, you probably know this stuff better than I do. But energy in general is the ability to do work or to be able to transfer heat from one thing to another. And when we're talking about earth systems and environmental systems, essentially we have to have energy to survive and thrive. Energy is absolutely necessary to maintain order in living things. Energy is needed to drive metabolism. And so energy is essential in any environmental system. Now, energy can come in a variety of forms. There's different types of energy. Sometimes you'll look at forms of energy in terms of the electromagnetic spectrum. And these are the different types of light. You have the light waves and you have the photons. The electromagnetic spectrum kind of ranges down here from lower energy radio waves all the way up to very high energy gamma rays. Here's where we find our visible light, the part that we can actually see. And then we have things like infrared, which we can use in detectors. Radio waves, infrared, not crazy dangerous. Visible light, not crazy dangerous. As we get up into these higher energy levels where you have these shorter wavelengths and higher frequencies, they're becoming more and more dangerous as we go through here. Ultraviolet radiation can be dangerous, X-ray radiation is dangerous, and gamma is very dangerous. And so these different types of radio waves or light waves, they come in different energy forms, but they're all different types of energy that can be utilized in environments. Some other forms of energy to know are potential and kinetic. And so potential is stored. This is energy that could be usable, but at the moment it is not. So like when you dam a river, we know that that river wants to flow. And so when you keep it from flowing, we are potentially storing that energy. If we were to remove that dam and that water starts to flow, then that energy would be converted into kinetic energy, which is the energy of motion. We also find potential energy in chemical bonds. So this is what we refer to as chemical energy. Foods are examples of chemical energy. And when we break them down and we break those chemical bonds, we are going to be converting that potential energy into other forms. And so kinetic energy is just energy of motion. We know that atoms and molecules are constantly moving around, and motion equals energy. Okay. Now there's different types of kinetic energy. It could be radiant. So radiant energy are like those radiation types that we looked at on the electromagnetic spectrum. Those light particles and light waves are in motion. It could be mechanical energy when machines or parts are moving. That river flowing would be mechanical. It could be electrical with our electricity, the positives and the negatives. It could be thermal related to heat. It could be sound. So there's all different types of kinetic energy. And when we measure temperature, we're just essentially measuring the kinetic energy that a substance contains. And so what's happening is that in these environments, in living things, we constantly have these energy conversions from one form to another. So like for example, in photosynthesis, we take light energy and we convert it into chemical energy. Or in cellular respiration, we take chemical energy in the form of glucose and we convert it into chemical energy in the form of ATP. Or we can use wind turbines to generate electrical energy. And so we constantly have these conversions going on, and depending on what type of energy you have, that's going to determine the type of life that can live in an environment. The environment kind of depends on the energy sources, and that will in turn determine the organisms that can be found there. Now with these energy exchanges and energy transfers, it brings us to some physics material, which once again, I'm not a physicist, I'm a biology teacher. And while I understand these, I am not an expert in any type of physics laws. But we do have two scientific laws in terms of thermodynamics. And thermodynamics has to do with those energy transformations. So the first law probably feels a little familiar to you if you've been in chemistry, because in chemistry there's a law known as the conservation of mass, and that matter is not created or destroyed. Well, this is the same kind of idea, but this time we're talking about energy and not matter. According to the first law of thermodynamics, energy is neither created nor destroyed. Instead, we can transfer it from one thing to another, or we can transform it from one form to another. But essentially, the amount of energy is constant. We're not adding or we're not taking away. We're not creating something from scratch. We're simply transferring or transforming the energy forms like we just recently talked about. Now, the second law of thermodynamics has to do with these transformations, and that every time energy is transformed, we are actually losing some energy in the process in terms of what is available to do work. Now, we're not losing energy in the universe, but we are losing energy in terms of what we can actually utilize to get things done. So for every energy transformation, the quantity is the same, but the quality of that energy and the ability to do something with it is going down. Now, another part to the second law of thermodynamics is this term called entropy. Now, anytime you start bringing up words like universe and randomness, it gets a little abstract. But essentially, entropy is the randomness of the universe. And every time we transform energy from one form to another, a lot of times that energy is going to be lost in the form of heat. And heat is a random energy source, okay? So every time we go through these energy transformations, the randomness or the entropy of the universe is going to increase, which means we're releasing some of that random energy known as heat. Now, if we're looking at a living organism or we're looking at a specific system, in that sense, the entropy or the randomness does not always increase. Anytime we create order, we're actually decreasing entropy. So I want you to notice that this is in the universe. So every time there's an energy transformation, the entropy of the universe is going to go up, because we will see a loss of energy in the form of random energy, such as heat. I know that's kind of confusing. Mainly just know the definition of the second law of thermodynamics. All right, now when we're talking about these energy conversions, we may talk about energy efficiency. And this is something we deal with in our homes. I know you guys probably aren't living on your own, so you don't really care about the electrical bill too much. But essentially, we want to be energy efficient. And we are kind of at a stage in our society where energy is a big topic. How can we reduce energy cost? How can we produce energy cleaner? There's all different things related to energy. But energy efficiency is essentially how well are we taking the energy and actually introducing that into our system to do work. So it's essentially a number measurement of the second law of thermodynamics. Because just because we have a certain energy type doesn't mean it's all going to be available to do work. So how much is actually available to do the work that we need to do? The energy quality is how easily we can transform that energy into usable energy for work. And so if we think about some of the different ways, like electrical energy, we could use the wind turbines, we could use hydroelectric, we could use water to generate it. We could use all different forms, but how easy is it to do that? And we also have to think about those things from an environmental perspective of just because it's easy, isn't necessarily safe for our environment. Now, when we talk about these energy exchanges, we usually talk about them in terms of systems. And we have two types of systems. They are either open or they are closed. Now, an open system is constantly exchanging between the system and the outside, okay? And so life is open, okay? Living systems are always going to be open systems. We are constantly exchanging with the world around us. Our cells are exchanging materials and energy with their outside environment. An organism, an ecosystem, they're all going to be open. A closed system is where all of these conversions of energy and matter are staying within the system. And in terms of life, closed system normally means dead. Okay. Now, we have a closed system in that we are limited within our atmosphere. In that sense, we kind of have some closed going on. But for the most part, anytime we're dealing with life, we are dealing with open systems that are constantly exchanging energy and matter with their surroundings. So the biosphere, here we have these exchanges. We have light coming in, we have heat going out. Photosynthesis, this is going to be an exchange between an organism and the atmosphere. With a closed system, it's completely contained. And so, like I said, normally when we're talking about life, we're going to be talking about open. Now, in order to kind of maintain systems and keep them going and keep them, just going and going and going and remaining relatively stable, we have feedback mechanisms. Because one thing is that, for the most part, we want systems to be somewhat in a steady state. And this is where they're kind of self-maintaining. They're not changing greatly over periods of time. If we do have huge amounts of change, that's definitely going to disrupt our natural ecosystems. So we really kind of want to shoot for a steady state. And the way we kind of maintain those steady states is through some negative feedback mechanisms. A lot of times, if we are experiencing positive feedback mechanisms, we are moving away from a steady state. And so these feedbacks apply to living organisms. In fact, in biology, we talked about negative feedback in terms of temperature regulation, osmotic balance, glucose regulation. But these negative and positive feedbacks can also apply to our natural environmental systems. So the key to negative is that it returns and stays in a stable state by kind of decreasing the rate of change. So negative involves kind of a turning on and then turning off, or kind of increasing and then decreasing. That's what makes it negative. It's not negative because it's bad. Positive is more of a turn on and turn up and amplify. So let's talk about an ecosystem for a second. Some of your negative feedback mechanisms are things like your cycles, your water cycle, your carbon cycle, your nitrogen cycle. Things like your predator-prey relationships. When the predators go up, they eat more prey, and the prey end up going down. Well, when the prey go down, they can't support as many predators, so then that kind of brings your predator numbers back down. And so once again, it kind of decreases that rate of change. It kind of goes back to a more steady state. Now with positive, this is where we have a turn on and a turn up. We see this a lot with some climate change things like the melting of the ice caps, melting of your permafrost. What can happen is when those things melt, it changes, it makes the surface darker, which means it absorbs more heat, which means it's going to melt more, which means it's going to increase climate change. And so we do see some positive feedback where we have an increase. Same thing happens with vegetation and erosion. If we lose vegetation, erosion increases. If we have more erosion, we have more drought, more dryness, less plants can be supported, and so we kind of get into a drier and drier and drier state with more and more and more erosion. So those are some examples of feedbacks within our environments. But essentially, in order to maintain a steady state, a lot of times we want to see these negative feedback mechanisms in our environments. So this is a throwback to the good old Amoeba Sisters. So positive feedback is an amplification. Negative feedback is kind of a turn on and turn off. So we decrease to go back to normal. All right, what is an ecosystem? Well, ecosystems are a combination of all of the living things, the biotic factors, as well as the non-living things, the abiotic factors within an environment. And so ecosystems could be something like a pond. An ecosystem could be the rainforest. They have sometimes well-defined boundaries, or in some cases, the boundaries aren't quite as exact, okay? Like a lake would have well-defined boundaries. The rainforest, not so much, okay? Now, each ecosystem is going to interact with other ecosystems around them. And as we mentioned earlier, in these open systems, we're going to have a constant exchange of energy and matter. And so these ecosystems make up the whole biosphere. which is essentially all of the ecosystems on Earth. It's your living Earth. This is where all of your life is going to reside, and your biosphere ranges from the deepest part of the ocean all the way up to the highest mountain peak, and that is the realm of life. Now, some important energy processes that you'll find in these ecosystems, some very important energy conversions that are occurring. One is going to be photosynthesis. Photosynthesis is essential for all life because photosynthesis takes energy from the sun, or solar energy, and it converts it into glucose, or carbohydrates. And these are going to be the main fuels for all of your living things. Now, organisms that we call producers or autotrophs are able to perform photosynthesis, and they are the ones that are essentially producing food for all life on Earth, including themselves, okay? Now, with photosynthesis, there's another perk. It's not the purpose, but another perk is that photosynthesis releases oxygen, which is going to be an important component in another important reaction of life. And that reaction is going to be cellular respiration. So we know that living things have to eat to get energy. Well, these two energy processes are ways of converting that food into an energy form known as ATP, which is energy for our cells. And so cellular respiration is what we call aerobic. This is the process that uses that oxygen. So organisms will take the glucose, and in the presence of oxygen, they will break it down into smaller components in a series of long reactions. And in that series of reactions, they're going to generate a pretty decent amount of ATP. We're also going to see that loss of heat there. Remember that second law of thermodynamics. So cellular respiration is really the most efficient way to produce ATP for living things. But there is another pathway for those organisms that do not live in areas where oxygen is present. And they essentially take the glucose, they convert it and break it down without oxygen in a process known as fermentation. And we get much less energy, where cellular respiration produces about 32 to 36 ATP per glucose. Anaerobic gives you about 2 ATP per glucose. So not nearly as efficient, but it's still a form of ATP production. And that takes us into our trophic levels. So we know that food is essential in an ecosystem. Organisms must consume food in order to produce energy. And so based on how they obtain their food, we put them into these different levels. So the two broad categories are going to be your autotrophs and your heterotrophs. Once again, autotrophs are able to make their own food, either by that process of photosynthesis, or there's another process known as chemosynthesis, where there's no light. But this word literally means self-feeder, okay? Auto means self, troph means feeder, so a self-feeder. They are able to produce their own food via photosynthesis or chemosynthesis. Everything else is going to be considered a heterotroph, which means different feeder. It's going to rely on another organism for its nutrition and energy. And so your consumers are going to fit into that category, as well as your decomposers. So we have our autotrophs, our producers. They are going to be at the base of every food chain or food web. They are the most important trophic level because they are able to create those food molecules like glucose. Everything else is going to have to get them from what they eat. And that's going to give rise to these different levels of consumers. So depending on what they're eating, they're going to fall in these categories. Now, you can be more than one. If you're not a picky eater and if you're an omnivore, there's a good chance that you're a primary, secondary, and at least tertiary consumer. So a primary eats a producer. So these are going to be plant eaters and plant and meat eaters. So if you eat plant material or you eat a producer, that makes you a primary consumer. A secondary consumer eats a primary. So they could be an omnivore or a carnivore. A tertiary eats a secondary. A quaternary eats a tertiary, okay? You don't usually see levels going much higher than this, and we'll talk about why here in a minute. But essentially, this is your basic food chain, food web. It starts with the producers. They're the most energy efficient. They are eaten by primary consumers, which are eaten by secondary consumers, which are eaten by tertiary consumers, which can be eaten by quaternary consumers. Now, a couple other groups just to think about. These are also going to be considered heterotrophs. Scavengers are those things that eat dead stuff. Now, they may not be consuming live animals, but they're still consuming. So they fit in that consumer category. Detritivores are organisms that break down tissues, like in the soils and things like that, and they consume as they break down. So they're not decomposers because decomposers absorb, but these are consumers that are kind of breaking down those small dead tissues, kind of like an earthworm or a dung beetle is another example. And then we have decomposers, which these guys, what they're going to do is they actually break down with enzymes things that are dead, and then they absorb the nutrition, okay? And that's going to include a lot of your fungi and some of your bacteria groups. But none of these organisms can make the food for themselves, and so therefore they fit in that consumer group. And so we represent these trophic levels with these diagrams like food chains and food webs. A food chain is just a very simple chain of events. A producer is eaten by a primary consumer, which is eaten by a secondary consumer, which is eaten by a tertiary consumer. Now, we put several food chains together, which is really more representative of an ecosystem, and that's where we get the food web. Okay? They can be very simple or they can be very complex, but if you can follow the arrows, you're able to follow the flow of energy from the autotrophs all the way up to your higher level consumers. Now, the main thing you need to remember is that the arrow is showing you where the energy is going. So the grass is eaten by the mouse is eaten by the owl, okay? The grass is eaten by the grasshopper, which is eaten by the frog, which is eaten by the snake, which is eaten by the hawk. So remember that that arrow says is eaten by, and it's showing that flow of energy through those trophic levels. Now, a couple other calculations that you might need to be familiar with. One of the things we measure in terms of ecological success is productivity. Now, this goes back to those producers. Remember that those producers are essential because they're essentially making those carbon compounds that everything needs to produce energy. And so productivity is a measure of how much are the producers producing, okay? How much energy is actually being made available, all right? And so we have what's called the gross primary productivity. So this is actually how much energy the producers are producing, pretty much how well photosynthesis is going, okay? Now, gross is the total. That doesn't mean that's available, okay? Think about your paycheck. If only we got our gross pay. But no, we don't. They have to take out for taxes. They may have to take out for insurance. So gross is the actual total, the total amount of energy that's converted into food by the producers, okay? And so we can measure that through the reactions of photosynthesis. But that doesn't mean it's actually available to everything because those plants, those producers, need that as well. So your producers are going to use some. So what we actually get is the net primary productivity. This is what's actually available to the rest of the ecosystem. So you take the gross, what the producers made, and then you have to subtract what the producers actually used for themselves, and that gives you that net primary productivity. And so this is kind of the measure of the success of an ecosystem. How well is the ecosystem doing? Well, how much food is being made? That's going to be a big indicator in the health of an ecosystem. Now, once again, we have efficiency. How well is that biomass being converted in that ecosystem? We can measure things like the standing crop, how much is actually available at a particular time. And then we can look at that ecological efficiency of how much is actually being converted into usable energy at the next trophic level. And the truth is, it's really not that much. Okay, your ecological efficiency is relatively low. Only about 10% actually gets passed to the next trophic level. So what happens is, some of that food is going to be used, so energy will be used by the consumer, or energy is used by the producer. And then when we have these energy conversions, remember every time we convert, we're going to have some of that energy lost in that random form of heat. Okay, so between use and heat loss, we only get about 10% being passed from one level to the next. And that gives rise to these trophic pyramids that kind of represent this energy loss. So the producers are the most energy efficient. they're only going to pass about 10% of that energy to your primary consumer, which will only pass about 10% of that energy to your secondary consumer, only 10% to your tertiary, only 10% to your quaternary. And you can see all we're doing is taking away a zero with each step. Only 10% is being passed. And so this is why you typically don't see anything higher than a quaternary consumer, because the higher you go, the less energy they're getting from their food. That usually means they have to eat a lot more as well, okay? I also want you to notice numbers in that you see how the pyramid is wider here? More grass, fewer grasshoppers, fewer frogs, fewer snakes, fewer hawks. So because there's less energy in the food, you can also support fewer numbers of those organisms, okay? So we can see this 10% exchange not only in energy values but also in actual biomass that can be supported. And that is going to finish up our lesson on energy in the ecosystem. Hopefully you got your notes all filled out, and you're going to be doing some activities to help you practice and study this. If you guys have any questions or concerns, once again, please feel free to email me. My email is on the syllabus. And I hope to maybe see you soon when I stop by PG. If not, hope you guys have a great day.